Hi, everybody. Welcome to our webinar, Electrophysiology Data Collection with Sutter Equipment. I'd like to go ahead and open up with this image. This is an example of essentially almost everything that we're going to talk about today. And I just want to walk through this and discuss some of the components and let this image outline our talk for us. Of the things that we're going to be talking about today, we will be discussing stages and translators. And in this particular example, we have these gantry style stages. We have another example that we'll see in a moment with much different style stages. This microscope itself actually has an internal translator that moves the objective. We'll see a very different example here in a moment. You also see manipulators, which are mounted on these gantry style holders. Right here we have a light source. This particular light source is an LED light source for the microscope, but we'll discuss a variety of different light sources. The microscope shown here is a SOM, but there's a wide variety of microscopes available for electrophysiology. So we're going to talk about some of the differences with commercially available microscopes, open platform microscopes, and so on. Of course, cameras are required to capture our images. I won't go too deep into cameras, but I will point out a few things that are important to consider for electrophysiology. And also tables. I'd like to point out that what we see here is not actually a table. This is just a platform breadboard in order to facilitate this photograph. The tables that we're talking about are vibration air floating tables, which we'll see a little bit later in the talk. At the very end of the talk, I'll also have a section on smaller details, if you will, that can really make a big difference to the electrophysiology experiment. So we'll point out a few tips and tricks that can really help everybody. I'd like to take a look at this other example here and show that we can have a very different electrophysiology rig setup. In this case, we still have stages and translators, but you'll see that it's a very different setup compared to what we just showed. This particular setup is using an Olympus BX51 microscope, which is mounted on a translator. We have different manipulators right up here. These are our MP285 manipulators. One thing I have not mentioned, which is kind of the most important part of the electrophysiology experiment, are the amplifiers for the actual data recording of the electrophysiology signals. In this case, I'm actually showing you 3 amplifiers, and as most of you know, the amplifier kind of goes in concert with the digitizer. For Sutter, we've designed our amplifiers to have the digitizer embedded in the unit itself. So what we're actually looking at here are not separate amplifiers and digitizers, but these are 3 separate amplifiers with embedded digitizers inside the unit. I'll talk a little bit more about what this does and the advantages that this has, but I do just want to point out that the 2 IPAs that you see on the top, these are 2 separate amplifiers. The one on the very top is a single head stage unit, whereas the second one just underneath it is a double head stage unit. And then we have a digital patch clamp amplifier, the silver unit underneath. So we're going to talk a bit more about these in detail and what it means to integrate that digitization in the unit itself. So the IPAs are optimized for whole cell recordings, whereas the digital patch clamp amplifier is optimized for single channel recordings. Let's take a look first at the IPA and double IPA, as we call it. The applications for the IPA and family include tissue slice recording, cultured cell experiments, in vivo patch clamping, network studies, adherent or dispersed cell line studies, and even complex experiments such as optogenetics, which require outputs from the amplifier itself. There are current clamp and voltage clamp capabilities of the IPA. For the current clamp, there is dedicated current clamp circuitry. This unit also enables bridge balance compensation and capacitance neutralization to remove the effect of the head stage from the actual experimental data. The voltage clamp capabilities include noise performance, an RMS noise performance of 1.4 picoamps. This enables the whole cell recording. Automatic and manual compensation are available, and I have to say here that the automatic compensation actually nails it every time. Our users that are using these systems for the first time are not used to that feature. That makes it a little bit more convenient to use. And these are based on a single feedback resistor. That's a 500 mega ohm resistor, which optimizes this for whole cell recordings, while keeping the design and the electronics extremely simple. So looking at our digital patch clamp amplifier then, and understanding what the differences here are, the digital patch amplifier can do everything that the integrated patch amplifier, the IPA, can, plus it can also do single channel recordings and has an extremely fast sampling rate of 5 megahertz for capturing fast events. Voltage clamp and courage clamp capabilities are included with this unit. Again, for current clamp, dedicated current clamp circuitry and bridge balance compensation and capacitance neutralization are available. And for the voltage clamp capabilities, it's important to note here that the open circuit RMS noise performance is actually under 200 femtoamps. This allows for the single channel recordings. And what you see at the top is actual single channel data. This is from a GABA receptor from a recent demo. Now, I want to discuss a little bit more about the integrated digitization in these units and what that does. So to do that, if I step back and we look at the flow of information in an electrophysiology experiment, typically what we start off with is the electrophysiology recording, which is fed into an amplifier. That then goes to a digitizer, and the digitizer makes sense of that waveform, puts it into a digital signal, which can then be fed into software for analysis so that we can process it and understand it and make meaning out of it. Meanwhile, the software also gives signals back to the digitizer, which can then be fed back to the amplifier for outputs. This can be useful for doing things like stimulation waveforms, for example. And then finally, under the traditional workflow of information, the software also communicates directly with the amplifier in order to adjust settings and whatnot of the amplifier itself. Now here, with these multiple components that are all connected via cables and connections, we set ourselves up for potentially a little bit of trouble. Not only is it a little bit more time consuming to install with all this cabling and connections, you risk the possibility of troubleshooting proper connections, wiring things incorrectly. But as many of you know who perform electrophysiology experiments, oftentimes there's a certain amount of troubleshooting and tracking down the source of things like noise, for example. You're generally tracing those sources through the cabling and through the connections of your system. What we've done at Sutter by integrating the digitizer into the amplifiers, we've dramatically simplified this whole flow of information. And so now if we redraw this chart, with an IPA as an example, instead of a separate amplifier and digitizer, what we see is that now we have the IPA and the integrated digitizer can essentially handle everything and communicate directly with, in our case, Sutter Patch software. So then what this allows is within a single unit, we still have our analog inputs for monitoring, say, environmental conditions such as temperature sensors. We still have analog outputs in each of the unit for providing waveforms for stimulation. And there's also TTL outputs for controlling other equipment. In addition, this integrated digitization kind of opens up the D-patch for this extremely fast sampling rate of 5 megahertz. It's also important to note that all of this is controlled with the Sutter Patch software. The Sutter Patch software is a full-featured software suite for controlling the amplifiers and collecting the electrophysiology data. Rather than getting into too much detail with the software here, I encourage you to go to our website and simply download a demo version. You'll quickly find your way around the software, and of course, we're available to answer any questions. I'd also like to mention that Jan, who did the generous introduction for me, he and Telly are both developers of the amplifier systems, and so we're honored to have them here on the webinar, and they will be available in the question and answer session. If you have detailed questions about the amplifiers or even the development of the amplifiers, they can probably answer most of those questions for you as well. Okay, so moving forward, I'd like to talk about manipulators and stages. It may not be completely obvious that these would be discussed in the same section, but it is important to kind of point out that manipulators and stages sort of go together. We'll talk about that more in the next slide, but keep that in mind. First, I'd like to start off with a little bit of historical perspective. This is called a Huxley manipulator. This is a very high precision manual manipulator that we started producing in 1985. The development of this manipulator actually goes back to Aldous Huxley's lab back in the late 60s and early 70s, actually. And a member from Huxley's lab met up with Sutter in the late 70s, and that's how the development of this manipulator started. Now that led to a more simple line of manipulators, manual manipulators for microscopes, and then on to our flagship motorized manipulators for remote control of the manipulator. In this case, this is the MP285. Many of you are probably familiar with the MP285. This has been our flagship manipulator for some time. This is a tried and true manipulator for many labs. With the MP285 and the MPC200 controller, one of the advantages of this system is that it can be controlled via software. We have a multi-link software that controls these. This actually integrates the control of the manipulators as well as microscope translators and stage translators as well, so that you can actually control the objective of the microscope, the position of each manipulator, and potentially the sample as well, and control all those in concert with each other. We also have a new line of manipulators. These have more simplified controllers, almost the same performance of the MP285, and a little bit higher stability, both mechanical and electrical stability, for keeping the pipettes extremely stable at the sample. I'll talk a little bit more about that a little bit later as well. So I mentioned that manipulators and stages go together, and the reason that is because you kind of have to think about the stage as being the home for the manipulator. The manipulator has to live on a stage. In the case of an inverted microscope, you need an extremely stable platform in order to mount the manipulator on. We have our MD series of stages for inverted microscopes. These fit most of the common inverted microscopes that would be used for research. And the key feature of these stages is that they bolt to the microscopes in a number of different ways to make them extremely stable. That's going to be really important for keeping your electrode stable in the preparation of the experiment. Additionally, and I'll go ahead and unfold both of these types of stages, there are platform stages, and then there are gantry and translator types of setups as well. In this case, I would say that experience probably drives most of our customers to request one variety over the other. Essentially, it's kind of what you're used to. Most of the time, an experiment does not require a platform stage over a gantry style setup, or vice versa. However, when you are setting up a system, you just have to think about how the sample is going to be controlled in relation to the pipettes and in relation to the microscope objective as well. And I mentioned multi-link earlier, that with our flagship MP285 series manipulators and the MPC200 controller, you could control a microscope translator, an XY moving stage, as well as the individual manipulators. So you could set up multi-point, multi-location experiments. You could have the manipulators go back and forth to different positions. You could have the microscope imaging at different positions while the manipulators were at other positions, and so on and so on. There's a wide variety of creative experimenting to be done here. Okay, so moving on to microscopes. Sutter has now started making microscopes for the electrophysiology experiment specifically. We've been making a number of models, such as the SOM, for some time, but we also have new models such as the Bob that you see here on the right. And let me just introduce both of these if you're not familiar with them already. The SOM is a very simple, as you see, kind of a fixed configuration microscope on the left. This can do some fluorescence, but it is very limited. It has a two-position filter cube, essentially. Small camera, as you see, a small condenser here. So somewhat of a limited setup, but sometimes smaller and simpler is better, particularly in electrophysiology. So that's popular for a number of applications. Meanwhile, the Bob, on the other hand, is also an open platform microscope that gives a lot of essentially open real estate underneath the microscope, with flexibility on how the microscope is mounted to the blue rail that you see there. This allows for setting the microscope up for all kinds of applications, so a very flexible design depending on how it's configured. There are gantry stages and platform stages. Some people might build their own sample holding apparatus underneath the microscope as well. The very open platform Bob microscope that is upgradable to two-photon microscopy in the same way that the DF scope is actually as well. So moving on to the DF scope and the MOM microscope, which you may have heard of. These are our two-photon systems. And with the DF scope, you might recognize that this is actually a modification to an Olympus BX51. So if we take a closer look here at this black box that is located between the filter turret and the eyepieces, this is the Sutter two-photon upgrade to the Olympus BX51. So this would enable the Olympus BX51 to do two-photon imaging, so deep tissue imaging. Meanwhile, on the other side, we see the MOM, the moving objective microscope, and this is a two-photon dedicated microscope. There are certain things that we can consider about each of the two-photon systems. For example, there are various scanner options. We have resonant scanners, galvo scanners, 3mm galvos, 6mm galvos, all for tuning the microscope for the appropriate application. You could say the same about the detector paths. We have 2-channel detector paths, 4-channel detector paths, short paths, wide 2-inch collection optics, for example, all with various trade-offs. If you have questions about these, we did a whole webinar on the two-photon systems about a year ago, which is available on our YouTube channel. And of course, we're always available to discuss these options in full detail. So furthermore, I'd like to point out some of the open platformness, if you will, of these microscopes. I'd like to take a closer look at the beam path here, in particular between the scan lens and the tube lens of the microscope. And if we just zoom in here, I'd like to point out that this is accessible to the user. So some modification and customization can be done by the user. This can be important for a lot of electrophysiology experiments where you're combining techniques and pushing the boundaries of what can be done together. So in this case, we see a polarizing beam combining cube, which has been placed in the center of the optical path here. Our primary imaging laser runs up through the periscope, through the scan lens, which is shown just to the right of the center here, through the left-hand side, through the tube lens, which is in the black tube on the left. If we want to bring in a second beam, for example, for doing second color simultaneous excitation for dual color imaging, or perhaps a second beam for photostimulation, for example, we could bring that second beam in through the side here with this polarizing beam combining cube, align the two beams, and there could even be a second set of scanners to independently control the scanning of that second beam setup. So this is just one example of how to modify the open platform beam path of the two-photon microscopes. So why is it called a MOM? Well, if we take a closer look at the head of the microscope, we'll discover that it is a moving objective microscope. So that means that the head of the microscope is actually mounted on manipulator rails so that it can move. Additionally, the microscope is mounted on its optical axis so that it can actually rotate around the optical axis. This is quite useful for experiments that involve animals where the objective may be better approaching a sample at an angle as opposed to straight up and down. So I mentioned some of the open platform flexibility of the beam path, but additionally, there are multiple places to bring in beams for this microscope, which can be used for all kinds of creative experiments. I showed you the beam access between the scan lens and the tube lens, where you could input a polarizing beam combining cube. But you also have beam access to bring an additional beam in behind the scan lens, and then additionally through the wide field vertical illuminator. And these beam paths are used all the time by our customers for very creative and unique applications. And one example is from Andy Shih, utilizing the beam path through the wide field side to approach the sample. Okay. So light sources. I think in the example in the beginning, I showed a little LED that was on the side of the microscope. But there's actually all kinds of light sources, as most of you know, that can be used for imaging. And in this case, we see two of our workhorses here. These are xenon lamp-based light sources. So xenon light puts out a wide, very broad spectrum, very powerful light across a broad spectrum. And our Lambda LS is sort of the workhorse xenon light source for microscopy. whereas the Lambda DG4 has some exciting features built in so that it can do very high-speed switching of the wavelengths of light that it's using and sending to the microscope. However, modern technology has given us brighter and brighter LEDs, and those are now quite suitable for microscopy imaging. And so we have a series of LEDs. This is the TLED and the TLED Plus. And we also have the FLED. So the FLED is essentially the same thing. There are white light versions, but also monochromatic versions. The FLED monochromatic versions are powerful enough to do very good fluorescence work. And lastly, to note on this slide, we have the HPX. This is a high-powered LED source. It is a broad spectrum source that puts out from about over 400 nanometers on up to about 630, I believe. So across the visible spectrum, very low maintenance, high power, very reliable and stable light source that replaces some of the white light systems. I don't want to talk in too much detail about any one of these because there's actually a new product that comes out that is sort of taking over a lot of the functionality of all of these devices and combining it into one. And that is our Lambda 421. So I'd like to spend a little bit of time talking about the Lambda 421 and how that's unique and what it can do. The Lambda 421 is an LED-based excitation device. It has positions for up to 4 LEDs, and then they're fed into a liquid light guide that you see here, shining the light on the table here. I'd like to take a closer look at the available spectra of the LEDs that are optional for this system. One of the limitations of LED-based products is the spectral range, but these are the LEDs that are available for the Lambda 421. What I've shown here is the visible range from about 390 to 700, and you see that we have plenty of LEDs that cover that visible range. But excitingly, we also have LEDs at 340 and 380 nanometers. Now, there's been 340 LEDs available for some time. However, in order to use them in a microscope for fluorescence work, for example, you need a very powerful LED. And I would say that this is the first time that we've had LEDs that are truly powerful to do experiments such as Fura experiments, for example, with reasonable exposure times. And in fact, now the new series of LEDs at 340 and 380 are quite bright, and you can actually turn them down and still get very good excitation and exposure times. In addition, on the other side of the visible spectrum into the IR, we also have a series of LEDs available here. This particular list is constantly growing and constantly updating. We like to spread the range of this as much as we can, as well as make sure that we're always including the highest power LEDs available. And indeed, this is the spectrograph that you'll see on our website, but there is actually one more addition to update that with, and that's a new 940 LED. So how does this work? How do these 4 LEDs combine into one? Well, if we look at the actual path here, we see the numbers 0 through 3 indicating 4 different LEDs, and they come through an output path. In this case, we have the first LED that shines directly through the output. The second LED shines towards the first one and bounces off of the first LED. So if we look at what sits in front of the first LED in this position, this is actually a bandpass filter that matches the spectral characteristics of the first LED, so that only the wavelengths of this LED are allowed to pass through that filter, and all other wavelengths will reflect. So what that enables us to do is bounce the second LED off of that filter, and in turn bounce the third LED off of those 2 filters, and in turn bounce the fourth LED off of those 3 filters, and all sent to the output. So it's all reflection based as opposed to a dichroic ladder, which runs the signals through the filters. Now that means you could also have any 2 LEDs on at one time. You could have any 3 LEDs on at one time. And of course, you could have all 4 LEDs on at one time. What's also interesting about it being reflection based is that you could actually swap, say for example, LED 2 and LED 3. You could swap their positions, the LED itself and its filter, and it would still perform the same. Now let's take a look at what that looks like. This is a little animation of how the light would come through, showing each of the 4 LEDs bouncing through and then all coming on. What might be a little bit more realistic is more unique timing that would represent an actual experiment. One of the advantages of this being an LED-based system is that the LEDs are directly modulated and they can actually turn on and off within the microsecond time range. This is a picture of the inside of the 421 beam combiner, and we actually see 4 different wavelengths of light kind of bouncing around in there and some of the scattered light coming back to the camera. It's a pretty image, but it kind of also gives you an idea of how these filters are all arranged inside. Now, looking on to cameras and detectors, I don't want to go into this too much because there's plenty of resources on cameras, but I will point out a few things that that might be useful for electrophysiologists to know. One, we do supply a camera from Q Imaging called the Electro. This is an electrophysiology specific camera. For example, it has an integrated grounding plug on the back to isolate the electrical noise. It has frame rates that are appropriate for video frame rate speed, for example. It has very good sensitivity and a fanless cooling, so very low noise, low vibration camera to facilitate electrophysiology experiments. I'd also like to point out the new backside illuminated camera from Photometrics. Essentially, this is an example of extremely sensitive SCMOS technology that's coming out from some of the camera companies now. Sometimes our samples will be extremely dim and we need a high sensitivity camera. These cameras now with SCMOS and backside illumination are reaching 95% quantum efficiency, which is extremely impressive. So if you have very dim samples, you might want to look at some of the higher sensitivity SCMOS cameras that are available now. This is the pretty new and groundbreaking technology. Additionally, sometimes those cameras on top might be a bit overkill for some of the experiments where we just need to get in and see a GFP labeled cell and move forward. We also provide these small STR cameras from Syntec. They make a range of cameras that are quite useful for finding samples, focusing, basic documentation, and even a little bit of fluorescence work. So moving on a little bit, this is a fun video of the P1000 in work. So micropipettes are an important part of the patch clamp process. The micropipette is actually what is going to approach the cell and do the patching, which, as most of you know, is a very finicky and delicate process. So being able to pull the precise pipette tip that you want and being able to do it repeatedly over and over is extremely important. And as you see here, the P1000 has very precise control that allows you to do that. Many of you might be familiar with the P97. It seems like as I go from lab to lab, I see a P97 in almost every lab I'm in. The P1000 is essentially the updated version of the P97. This has essentially a touch screen and a lot more automated functionality, including built-in pipette recipes, for example, storable programs, and so on. The P1000 is not the only pipette puller we make, though it is likely the most appropriate for the people in this audience. But I do want to point out that the P2000 is a laser-based pipette puller. This opens the door to pulling pipettes out of a larger variety of materials, essentially. And then we also have a very basic P30 pipette puller as well. Okay, I had mentioned that at the end I would give some tips and tricks. That's going to come into play in this section where we start talking about stability and isolation here. So I've titled this Air, Quartz, and Stainless Steel. So what are we talking about air? Well, in air, I'm referring to the anti-vibration tables that are actually floating on air. Obviously, usually these are needed for these types of experiments in order to isolate the imaging system from the vibrations that are in the building. And sometimes if you have stability issues, it's a common problem for these tables not to be adjusted quite properly. So it's worth checking to make sure that the table is indeed floating at every corner and is actually isolating you from the vibrations in the building. Please contact me if you have questions about how to check these things, because it can make a big difference to the experiment itself. Also available are Faraday shielding cages. which can help dramatically with isolating the electrical interference from the experiment area. Now, thermal drift and actually pipette drift is a bit of an issue. So when people are designing these components for these systems, particularly the things that hold the pipettes, one of the things that comes into the designer's mind is, how do we make this stable, stable, stable? Well, when a pipette is attached to a cell, if it's attached there for quite some time, that pipette may drift, and some of that drift can be due to thermal stability, so thermal expansion. If we look at this manipulator, it's made out of aluminum, and aluminum does have an expansion coefficient. So as the temperature in the room changes slightly, the aluminum can either expand or contract slightly, which then moves our pipette tip, which can be detrimental to our experiment. If instead we utilize a different material, we can actually reduce that thermal drift considerably. So in this case, we actually have a stainless steel version of our Trio, the Trio designed for high stability, which adds even more stability to the manipulator itself. I warn you, it also adds a considerable amount of weight. However, the thermal expansion coefficient of the stainless steel is about half that of the aluminum, so the stability that you get is noticeable. One of the other things that we found actually is that with the pretty intense weight of the stainless steel Trio, that tends to dampen some of the vibrations as well. So if we've had these set up on flimsy tables at vendor shows and whatnot, where there's a lot of vibrations on the table and on the floor, it's not isolated by an air table. And then we'll have a pipette in the aluminum manipulator and a pipette in the steel manipulator, and you can actually see that that steel manipulator actually blocks a lot of the vibrations from getting to the pipette. It's almost as if the tables at these trade shows are vibrating around the manipulator itself. Now, if we're talking about the manipulator and thermal expansion, as we've kind of investigated the properties of a electrophysiology setup to find some of the problematic areas for these types of instabilities, we noticed that the head stage, and in particular the pipette holder itself, is a source of some of these instabilities. So what we've done is we've actually developed a quartz pipette holder. This is a relatively small component, but it can make a really big difference. So how much of a difference can it make? Well, we set up a little test procedure to put a heating filament underneath the head stage of the pipette. And we did this test with both pipette holder types placed above the heating filament. And what we found is that the polycarbonate pipette holder was very, very quickly, almost immediately, this is a 2-second heating cycle of the filament that's placed under there, is displaced extremely. We see it move almost out of the field of view of the microscope area here. Whereas the quartz pipette holder is virtually completely stable. If we look at the expansion coefficients, the thermal expansion coefficients between polycarbonate and quartz, we see that there are dramatic differences. Quartz material is about a factor of 100 times more stable according to the thermal expansion coefficient. And indeed, that's shown very well in these images. Now, we are getting down to the nitty-gritty of the details, but each one of these details adds another layer of potential problems or potential solutions, depending on how it's engaged. So what we're looking at here is the actual, the tip of the head stage. These are the threads on the end of the head stage that the pipette holder will thread onto. It's important here to note that the cap of the head stage, the Teflon connection that threads over this, if you're mounting Teflon to Teflon, this does not create a very stable surface. If you're mounting Teflon to things, generally you want to have a harder, more solid and rigid surface that it's being mated to. And in this case, we've made our head stage threads out of aluminum, and this does provide not just more stability, but it turns out also an added layer of electrical isolation. We were surprised by this, but it makes a little bit of sense that this is a sensitive spot to electrical noise pollution. I think since I've taken you down the road of looking at the threads of the head stage, I think that might be a pretty good place to start wrapping up. So I'd like to thank you for your attention and for going through these slides with me. I'm very excited about these products. I've got one more device here that didn't quite fit into my talk, but I'm also very excited about it. So I wanted to just point it out for a moment, just so that you're aware of it. This is something that we call the VF5. This is an interesting device that can be used in conjunction with our light sources to actually select a tunable bandpass of excitation light from a broadband excitation source. If you'd like to learn more about this, please feel free to contact me offline. But this has been used in some very interesting hyperspectral imaging experiments and things like that. So basically it has the ability to tune bandwidth across the visible spectrum at any arbitrary wavelength from a broadband source. So pretty exciting for some specialized experiments. And on that note, I think I'd like to open it up to some of the questions.
Thank you very much, Jeff, for this instructive presentation. We have received a number of questions during the talk already. Telly will host the Q&A session.
Great, thank you, Jan, and thanks for the talk, Jeff. So we do have a couple of questions, so let's start off. Here's a question regarding the LEDs. In the age of LEDs, is there still a reason to use a conventional light source?
Yes, but that argument is becoming harder and harder to make every day.
Is there any particular applications where...
I can think of some right off the bat where, for example, more than 4 channels of excitation might be needed, in which case you would be better served by a xenon light source and potentially a high-speed filter wheel, for example, that could open up to maybe 10 different excitation wavelengths as opposed to being limited by 4. So that's a potential application area where one might still turn towards the xenon lamps, for example. Cost can also be another driving factor. The Lambda LS is a fairly cost-effective solution when you're incorporating it into a microscope, whereas the individual control for the 4 LEDs, it adds a little bit more cost in the product. So, if it's a budget-constrained system, for example, that can be another argument for going with the xenon sources. Although there are very simple LED sources as well, so if you're only looking for 1 or 2 channels, again, you can potentially configure a very simple LED source that can be cheaper than a xenon source at that point.
Yeah, great, thank you. Here's another one for you. Is it possible to record from dissociated cells or cell cultures from an upright microscope? For example, like the Bob or the SOM that you showed earlier?
Indeed, I know that it is. I might enlist Jan's experience for a little extra comments on what the trade-offs there are. Jan, do you have some points to point out?
It is possible with some limitations. If you want to use the same rig to record from both slice or tissue slices, brain slices, or slices from other tissue, and dissociated cells, cultured cells, adherent cells, then you definitely want to use an upright microscope if you don't have the option to use an upright microscope on one rig and an inverted microscope on the other rig. You need water immersion objectives, obviously, with certain limitations that it definitely is possible to use that on an upright microscope, including the SOM and the Bob. What you cannot do is record slices on an inverted microscope, because you would have to, in essence, focus to the entire tissue, and that degrades the image quality to a point where it's tricky, to say the least. It has been done, but wouldn't do that.
Well, here's a question that I'll probably take on myself, and they want to know if the IPA or the D-patch amplifier can control the timing or intensity of the light sources, including the Lambda 421. The answer is yes. So both the IPA and the D-patch do have auxiliary outputs as well as TTL outputs that can be controlled by the Sutterpatch software, not just by setting a value, but we could actually create all sorts of custom waveforms to drive the device to actually regulate all of the timing. So yeah, that's quite easy, and not only for light sources, but all sorts of other systems like perfusion systems, for example. There's another one for you. You showed the quartz pipette holder. Does it have advantages in terms of electrically being quieter than the polycarbonate holder?
I might turn that over to Jan if he's got some comments on that. I know that the aluminum threading on the tip of the pipette does provide some electrical insulation. I'm not sure about the quartz at the other end, though. Jan, do you have a comment there?
Yeah, the dielectrical properties of quartz, if you use it for pipettes, make the recording quieter. And of course, we were hoping that making the pipette holder out of quartz, the barrel out of quartz, would also make a difference. Unfortunately, we have not been able to detect any significant differences in noise performance between the polycarbonate barrels and the quartz barrels. As much as I would love to say they're quieter, it does not look like it. They're definitely not more noisy. It kind of makes sense since the quartz is not in touch with the electrolyte, with the pipette solution directly, or with the bath solution for that matter. So it kind of makes sense that the impact on the noise performance is a little smaller than with the pipette material. But yeah, I would say electrically they're at least identical to the polycarbonate, but the big difference is definitely in mechanical stability.
Great, thank you, Jan. Here's another one. The Lambda 421, you showed it with the LED light sources. Is it possible to use other light sources like a laser?
Actually, indeed it is. So at the heart of the Lambda 421 is something that we call the OBC. And when I showed an image of the rainbow colors where you could actually see the four bandpass filters in the output port, what we're looking at is actually the OBC itself. So if we just isolated the OBC, the beam combining part, and drop the controller, for example, you could potentially utilize that OBC to combine any four light sources. One of the easier ways to do that would be through liquid light guides, just combining collimated liquid light guides and attaching those to the beam combining pentagon, as we call it, due to the 5-port configuration. So that would be one of the easiest ways, although you could couple other light sources onto the Pentagon beam combining cube directly with the appropriate adapters, which we likely have for you. And we've had a number of folks ask about using it for lasers, for example, either in custom applications or potentially even OEM applications. And that's also possible, but I have to add one caveat there, that the laser alignment would have to be done externally, or somehow a different modular component would have to be mounted to the edge of the optical beam combining pentagon, if you will, in order to align and combine those lasers.
Okay, great, thank you. Actually, there's a couple more questions that just popped up that I would like to see if I could tackle. So the first one is, in the integrated design of the EFIS amplifiers, also has consequences concerning repairs, exchange of parts, etc. Any comments on the lifespan of the amplifier and what happens if the digitizer breaks? So I'll take on this question. So one, the amplifier design and the amplifiers themselves are new to Sutter. So we don't have many years of experience on the field to really be able to say what kind of lifespan these amplifiers will have. I would believe that based on experience from other equipment that we have designed, that it's going to be pretty long life. Yes, indeed, it is a combined integrated system. So swapping out digitizer or parts may not be so simple. Actually, it's not possible, other than head stages. Head stages are separate items. In fact, for the D-patch, the preamplifier section, the analog section that's mounted to the head stage, is a separate box, a separate entity, and in that entity it has the calibration constants and its own independent A to D and D to A converter for that particular head stage. So those can be easily swapped around. If something is damaged there, there's no need for calibration because everything is stored in an internal EEPROM. So those can be easily changed, swapped out. And one other thing that this is an integrated circuit board, so the whole design is on a single circuit board. Unlike other designs that I have seen and worked with in the past that have had many interconnects, most of the failures that I have seen in the past have always dealt and been around these interconnects. We don't have any of those, so we think that this concept, this design, this single board solution, actually would lead to a really long lifespan on these products. So another question that we have regarding, again, the software, do you generate ABF files that can be used by ClamFit and other analysis software? We do not generate ABF files, but we do generate ABT files, which are the text version of those files. In particular, we find that the Igor files that we use, because SutterPatch is built all on top of Igor Pro 7 and the newly released Igor Pro 8 very shortly, that there's a lot of different ways to get this data set out into other applications. And with that, that is the end of the questions that I see here in our panel. Any additional questions, we'll be more than happy to answer via email.
If anybody has further questions, Jeff's email address is up on the screen right now. Feel free to shoot him or Telly, who is telly@sutter.com, or myself, jan@sutter.com, an email with any further questions you may have, any comments. I would like to thank everybody in the audience very much for attending and for your attention and for your questions, of course. And I'm looking forward to seeing you either in person or at another webinar or a scientific conference sometime soon. Thank you very much. Goodbye.